Okay, let's get started. How's everybody doing? You know what final project I would like is, so we can drive a VGA screen from these Picos. Wouldn't it be cool to put a Pico, so you plug a VGA screen into your computer, there's a Pico that sits between your computer and the VGA that communicates with some kind of a vision system, so that you could put a camera on that and it would see my face and block out the pixels here so that I would just have like a square shadow. I think you could do that. It'd be a really cool project to try. I'm like, got blind spots now. So my plan for today is I want to start talking through the content that's going to be of relevance to you in your checkouts this week. I'll just remind you that the objective for your checkout this week is, last week, am I recording? Last week, you got crickets chirping, so you were synthesizing sound. The objective for this week is to interface a microphone with the RP2040 so that you can hear the sound around you. And then you'll use that microphone and an FFT algorithm to detect other crickets. So in addition to generating cricket chirps, you'll be able to detect cricket chirps. And the objective for this week is limited to that. The notion is that core 0 will be able to detect the chirps coming from core 1, but it won't detect its own chirps. And core 1 will be able to detect the chirps coming from core 0, but it won't detect its own chirps. So there has to be some sharing of information between your interrupt service routine, keeping track of am I chirping or am I not chirping, and the section of your code that's sampling the ADC and doing the FFT analysis. But we'll talk through and contextualize all of this. What I want to do before getting into that lab-specific stuff is just talk a bit about the ADC in general, and then talk a bit about DMA, direct memory access in general. This is really just an introduction. As I hope will become evident, there's a lot that we can talk about with DMA. It enables a whole lot of interesting stuff, but I want to just introduce it today. And then I want to talk about getting the two to talk to one another. So let's start with the ADC. The RP2040 has an onboard 12-bit SAR ADC. SAR stands for Successive Approximation Register. And this is a picture from the data sheet that's giving us a high-level schematic view of how this ADC actually works. So what you can see here is there's a 5-input MUX into the ADC. 4 of these 5 inputs can be mapped to GPIO pins to interface with the outside world. The 5th one goes to an internal temperature sensor. So you could measure the internal temperature of the RP2040 if you wanted to. Incidentally, I thought about including this in Lab 1 because, as those of you that have been reading the lab assignment would have noticed, these crickets change their frequency as a function of temperature. So in a subsequent year, it might be the case that we use this so that if you squeeze the RP2040 and it warms up, you hear the pitch shift. I think that would be kind of cool. Try to model it after the biological ones. So in any case, there's this 5-input MUX, which goes into a sample and hold register. What this sample and hold register looks like is inside of this box, there's a small capacitor. The capacitance across the input of the ADC here is 1 picofarads. There's a small capacitor here. The notion is that when you close one of these switches to the MUX, that capacitor charges up to the voltage of the input. And then that switch opens, and you've locked in the voltage that was on the input on that capacitor. And then this goes into this successive approximation register, where you can see the sample and hold register communicates to a comparator, goes to one input of the comparator, and the other input of that comparator goes to a DAC that's controlled internally. So what happens here is we're looking at this voltage in the sample and hold register. The DAC, suppose we're measuring voltages in the range of, just to make the math easy, we'll say 0 to 3 volts. What the DAC would first do is check, okay, is this voltage greater than or less than 1.5 volts? It would check the most significant bit. The capacitor would either snap high or low, informing the system whether the voltage that we've sampled is greater or lower than the voltage that the DAC is generating. And then it would go to the next most significant bit. It would start going down the bits in order of significance until it had narrowed down the voltage on that capacitor to within 12 bits or so. So it's successively approximating the voltage that is stored on that capacitor. The system works by charging up, incidentally, by charging up an actual capacitor, right? Which suggests that there is actually some maximum rate at which you can accurately sample the ADC, because you have to actually wait for the voltage on that cap to charge up. So on this system, you can sample the ADC as fast as 500 kilosamples a second. That is to say, you can do a sample every 2 microseconds. The ADC on the RP2040 has its own clock. It runs off of its own 48 megahertz clock. And every time you sample it, a single sample will take 96 cycles of that 48 megahertz clock. So you do the math, and that turns out to 2 microseconds per sample. Some other things to just note about this system. Let's see. So it's a 12-bit DAC. The effective number of bits is 8.7. That is to say, beyond 8.7, beyond 8 or 9 bits, it's mostly just noise. The effective number of bits here is 8-ish, 9-ish, 8.7. Everything else is mostly noise. By the way, like, is that reasonable? That's an ill-posed question, but what should we expect from an analog to digital converter inside of a microcontroller? With an effective number of bits of 8.7, that's giving us a resolution of what, like 8 millivolts or so per ADC unit, per effective ADC unit. The thing to keep in mind is just that this ADC isn't existing in isolation. It lives inside of a chip with a bunch of other stuff going on. There's current flowing, there's gates flipping. All that stuff is generating some amount of electromagnetic noise, which is inducing some amount of voltage on the inputs here. So to expect more than something around here from an ADC in a microcontroller might be asking a lot, okay, without maybe doing a whole bunch of work. But that seems about reasonable. Incidentally, if you go online, there's some Good Samaritan who has done a really extensive analysis of this ADC. It's really interesting to read if you care about such things. There's a 4-element receive sample FIFO, which you can enable or disable for this system. So you can have the ADC dump its samples into a FIFO, and you go retrieve the measurements out of the FIFO. As we'll see, we're going to use that for interfacing this with the DMA channel. The DMA channel will access the FIFO. And it has an interrupt generator and a DMA interface, of course. You can set this up in a variety of ways. I'm going to show you this in code because I think that's the clearest way to talk about it. But you can set up the ADC such that you do what they call single shot sampling, where you just say, give me a sample off this mux input. You can set it up in free run sampling, where you configure, there's a timer associated with the ADC. You configure that timer to the frequency with which you want to sample the ADC, and then it will just generate samples synchronously with that timer and pop them into the FIFO. If the FIFO fills up and you don't clear it before the ADC generates the next sample to pop into it, the way this system handles that is it retains the old data in the FIFO and the new data just gets thrown away. You can also set this up for round robin sampling. So you can say sample this input, then this one, then this one, then this one, then go back to the first one. So this is an overview of how this works. And I'd like to go next to some code to take a look at how we actually configure this thing. So let's go, as usual, to the course demo code, incremental example. And I want to take a look at the example project from which you'll start your checkout this week, which is the FFT demo. And if we take a look at this, we're going to talk through other aspects of this in just a bit, but I'd like to go down to main first just to see the ADC configuration, setup and configuration. And what I'll say is that the ADC configuration that you see in this project in particular is as complicated as this configuration will ever be. And it's not that complicated. But it's because we're configuring the ADC in order to interface with the DMA channel, so it requires just a bit of extra work and configuration to get these two things to talk to one another, as we'll clarify in just a moment. If you just wanted to set up the ADC to sample in software, say give me a sample, it would be much simpler than this, and I'll talk about the stuff that would get omitted. But in order to set up the ADC, we go through the following sequence of events. We first call ADC GPIO init with a GPIO pin. We're calling it with ADC pin, which if we scroll up to the top, we'll see is mapped to one of the GPIOs. Let's see. ADC pin is mapped to GPIO 26. It may not be necessary, but let me just justify that for a second here. Whoa, what happened? So if we go to, what is happening? The high Pico data sheet. I think this actually is worth clarifying. So I mentioned that there's a 5-input mux into the ADC. If we look at the pinout for the Pico, what this shows us is that ADC mux input 0 maps to GPIO 26, mux input 1 maps to 27, 2 maps to 28, and one of them goes to the internal temperature sensor. The other one's here someplace, don't know where. But in any case, that's why we're mapping it to GPIO 26. And just get back to where we were. What this does, incidentally, when we call ADC GPIO init, for each GPIO pin, there's a bit of circuitry associated with that pin that controls how it interfaces with the outside world. And if we want some details about that, we can take a look at the RP2040 data sheet. I want to show you this just a second. And I want to look in particular at the pads section of the GPIO chapter. So if we go down to GPIO and take a look at pads, what this is showing us is for each GPIO pad, there's a bunch of stuff that we can turn on or off associated with that pad. So for instance, you can see that there are pull up and pull down resistors that are attached to each of the GPIO inputs, which, as many of you have discovered last week, you can turn on to have an internal pull-up resistor. That's useful, as many of you found in the week 2 checkout for doing things like interfacing with buttons. This allows for you to not have to breadboard an external pull-up or pull-down resistor. You can use an internal one. That's nice. And there's other stuff in here too. There's a comparator that you can turn on or off, and there's some circuitry for controlling the output slew rate and such. It also allows for you to configure things like how much current can you source from the GPIO port. In order to use one of these GPIOs as an analog input, all of the digital functions associated with that GPIO pad have to be turned off. And as always, you could do that by going in and doing some register manipulations associated with that GPIO input. What that ADC init function does is it does all of that manipulation of the circuit on the GPIO pad automatically. So in particular, it turns off all the digital stuff associated with that GPIO and enables the analog stuff associated with that GPIO. The next thing that we do is call ADC init. That resets the ADC. It turns on that 48 megahertz clock that the ADC uses. And it takes some time. There's a phase lock loop associated with that clock that takes a little bit of time to stabilize. It doesn't turn on instantaneously. There's a control and status register with a particular bit that will go high when the system is stable and ready to go. This function, when you call it, will sit and block until everything's stable. So you call ADC init, it sets up the ADC clock. It won't allow for the code to proceed past that line until everything's good to go. So this sets up the clock and resets the ADC. We then select which of the mux inputs we want to go into the ADC. So this is something that's perhaps an easy step to skip because it feels like we've already done some sort of ADC to GPIO configuration. The other configuration that we need to do is in that, let me just pull up the ADC image here. We need to tell the ADC which of the mux inputs we're accessing. we're using GPIO 26, which maps to mux input 0. If we wanted to use GPIO 27, as we just saw in the pinout, we would map to mux input 1. Let's see here. So we turn off all the digital stuff on the GPIO. We reset the ADC, turn on the clock, and wait for it to stabilize. We tell the ADC which of the mux inputs we're going to be sampling from. If we were setting up round-robin sampling, we might select a few of them. In this case, we're just sampling from one of the ADC inputs. And then the next thing that we do is configure that 4-sample deep ADC FIFO. And this too, I'll walk through this. There's quite a bit of configuration that you can do with this FIFO. Not tremendously much, not so much that it's incredibly annoying, but it requires some thought. So this FIFO is set up for interfacing with the DMA channel. If you weren't trying to interface the ADC with DMA, you might set this up somewhat differently. But in order to get it to talk to DMA, we do the following. The first argument to this being set to true, what this does is turn on the FIFO. It writes each completed conversion from the ADC to that FIFO. If that were false, it wouldn't write the ADC conversions to the FIFO at all. We would just go access it from a register called result, I think, where the ADC sample, the converted ADC samples go. We then turn on the DMA request signal. I'll talk about this more in a moment, but among the configurations that you have to set up for a DMA channel are, you of course have to tell it where do you want, a DMA channel, I'll just remind you, moves data from one place in memory to another place in memory. There's a bunch of configuration associated with that. Clearly you have to point it to where you want it to go get data from. You have to point it to where you want it to move that data to. You also have to tell it how many transfers to do and how should it pace those transfers. Do you want for it to just move that data as fast as it can? Or do you want for it to move 32 bits of that data every microsecond? Or do you want for it to do a transfer whenever it receives a signal from some peripheral that it's communicating with? In this case, we want for the DMA channel, as we'll see in the configurations in a moment, to move data from the ADC FIFO to a buffer in memory where we're going to run an FFT. So we only want for it to move data from the ADC FIFO to memory when there's actually something in the FIFO. And turning this on allows for us to configure the DMA channel such that it will do transfers paced by the ADC FIFO. Whenever a sample appears in the FIFO, this data request signal will be asserted, which tells the DMA channel, please do a transfer. The DMA channel will go grab the data from that FIFO and move it into a sample buffer. This argument, remember it's a 4-sample deep FIFO. We can configure how many samples we would like for there to be in that FIFO before that data request signal is asserted. So if we only want for that DMA channel to be activated, that's a bad example. In our case, when we're setting up a DMA channel, we want for this to be asserted every time there's a sample in the FIFO. Every time something appears, we go and get it out, which means there's never going to be more than one sample in the FIFO. We're never going to allow for it to fill up. If instead of interfacing this with the DMA channel, you were doing something like you wanted for an interrupt to be thrown when the ADC got a sample, instead of for a DMA channel to be activated, it may be the case perhaps that you only wanted for that interrupt to fire when there were 2 samples in the FIFO or 3 samples in the FIFO so that you don't take the interrupt quite so often. In our case, since we're interfacing with a DMA channel, and none of this is requiring any CPU interaction anyway, we're going to have it grab the sample every time it appears. This argument, we can optionally have the 12th bit of the ADC sample be an error bit, which is that bit will either be 1 or 0. If it's one of those, it indicates that there was an error when it gathered that ADC sample. If it's the other one, then it indicates that there was no error. What we're going to see in just a second is to interface this with the DMA channels. DMA transfers can occur in 8-bit chunks, or 16-bit chunks, or 32-bit chunks. There is no 12-bit chunk option. So this final argument here shifts out the bottom 4 bits of each ADC sample so that we only retain the most significant 8, so that we can get it to talk to a DMA channel that's configured to do 8-bit data transfers. So we're losing some information here, but as we already saw, the effective number of bits for this is only 8.7 anyway. So most of the stuff that we're getting rid of here is noise, and we're retaining the most significant 8 bits. So this is all setting up the FIFO. Incidentally, if you were just, say, sampling the ADC in an interrupt service routine in software, you wouldn't have to do any of this. You could just call GPIO init, initialize the ADC, select the input, and then there's an argument in the function in the SDK guide, so something like ADC read or something like that. Yeah.
What if the ADC pin and ADC channel don't match?
If the pin and channel don't match, does it throw an error? I don't think it does. I think what would happen is, let me think about this. So the errors would be the GPIO pin associated with the MUX input that you've chosen might still have some of its digital stuff turned on, which would screw up your measurements from that MUX input. So I think the symptom would probably be this data doesn't make sense. I think that would be the symptom. Okay. The next thing that we do here is I mentioned that there's a timer associated with the analog to digital converter, which allows for us to set up how frequently we would like for samples to be gathered. And in this case, we're saying we would like for samples to be gathered at the following rate. The ADC clock rate, 48 megahertz. If we look further up in the code, we'll see a pound-defined ADC clock, 48 million, divided by our desired sample rate. This, for our purposes, let's see. We're using an FFT to detect cricket chirps. Our cricket chirps are at 2300 hertz. At least how fast must we sample the ADC? At least that's the Nyquist sampling limit, right? So this needs to be, for us, at least 2 times 2300 hertz. I think by default, this is set up at, I have it configured in the example to be 10 kilohertz, which means you'll be able to measure power in frequencies up to 5 kilohertz. And then up in the code, up in one of the threads rather, we actually turn this thing on, turn the ADC on. That occurs in line 195 there. When we call ADC run true, what that does is turn the ADC on in the free running mode, where what it's going to be doing now is every time that timer overflows, which we've just configured, we've configured it to overflow at 10 kilohertz. So 10,000 times a second, the ADC will grab a sample, it will take a measurement, pop that measurement into the FIFO, and assert a data request line for a DMA channel to come retrieve that data and move it to a buffer. We're going to look at the DMA channel next. Questions about this, though? As far as ADCs on microcontrollers go, there's not that much configuration required here. It's a pretty easy one to use, actually. And as I mentioned, this configuration that you see here, this is as complicated as the configuration really ever gets. I suppose maybe if you were doing some kind of crazy round-robin sampling of ADC, you could hallucinate some application that was more complicated than this. But for many, many of your applications, it probably won't get more complicated than this. This is what we do to interface it with a DMA channel. Okay. Any ADC questions before I start talking about DMA? We're going to come back to this a little bit when I start talking about getting the two to talk to each other. Okay. So then, let me remind you what DMA is. DMA stands for Direct Memory Access. There are a lot of things I hope you take away from this class. One of the things I would really like for you to take away from this class is how powerful it is to use these DMA channels. I'm going to introduce them today, and then throughout the semester here and there, I'm going to do a couple of sort of case study examples of applications that are only possible through utilization of DMA channels. So hopefully that appreciation builds throughout the semester. But this is a really powerful peripheral to understand. I'll just remind you that all that a DMA channel does, it's a bus master, so it issues bus commands much like the processors do. And it's a very simple coprocessor. Each DMA channel is a very simple coprocessor. It moves data from one place in memory to another place in memory. And it's up to you to do all the configurations. How much data does it move? Where does it look to get the data? Where does it put the data? What paces the transfers? How many bits are each transfer? All that's configuration that's up to you. But fundamentally, you're taking information from one place in memory and putting it in another place in memory. The power of this on a microcontroller is that all your internal hardware peripherals are memory mapped. The ADC, for instance, when it takes a sample, that sample goes to a place in memory with an address. And you can point a DMA channel to that address, as we will here in just a moment. So you can move data from peripheral to memory, ADC to memory, as we will this week. You can move it from memory to peripheral. I can show you an example of this in just a moment, but you could, for instance, store a sine wave in memory and have a DMA channel with no CPU interaction, shuffle that sine wave out to the SPI transmit buffer, and you would generate a tone without calling any interrupts. If you're trying to do something like generate sound effects for a video game, that's a good trick to know. You store all your sound effects in memory. When some event in your video game occurs that you want for there to be a noise associated with, the ball bumps into the wall and you want to boing, or something like that. If you set up a DMA channel to do that, you don't have to take any interrupts and waste time that you would otherwise like to spend doing animation on doing audio synthesis. You just say DMA channel go, and it moves all the data from memory out to the DAC with no interaction. You could move information from memory to memory. So you could move it from one buffer to another buffer, sort of a behind the scenes mem copy. I haven't tried this yet, but there's no reason as far as I'm aware that you couldn't alternatively move it from peripheral to peripheral. So perhaps you could set up a DMA channel to grab data from the ADC sample buffer, paste by the ADC receive FIFO, and move it to the SPI transmit buffer. And if that SPI channel is communicating to a DAC, you could probably set up full audio loopback. That is, say, talk into a microphone and have your voice come out of a speaker without even involving either of the processors, using no CPU time. It'd be kind of cool. And it's up to you, as I've mentioned, to do all the configurations associated with this fundamental capability. So you configure the transfer size. Are we moving data in 8-bit chunks, 16-bit chunks, or 32-bit chunks? Where are we moving the data to and where from, and where are we moving it to? There's some details associated with this, as we'll see. You can configure, say you want a DMA channel to do, 100 8-bit transfers. You can say, I'd like for you to start at this address and then walk in 8-bit increments forward in your read address or in your write address. If you're trying, for instance, to move a sign table from memory, you don't want to always be accessing the first index of that sign table. You'd like for the DMA channel to automatically walk through the table. You can configure that. And it's up to you to configure the start condition for each transfer and for the DMA channel. Do you want for each transfer to be triggered by an internal timer? There's a timer associated with these DMA channels. So you can say, send a transmission to the SPI channel at 40 kilohertz, because I'm doing audio synthesis. You could set that up. Or you could have it be triggered by one of the other hardware peripherals, as we are this week. I'm triggering it off of the ADC. You can also chain DMA channels. You can say, I'd like for DMA channel 1 to start when DMA channel 0 finishes. And you can chain it back then, too. And then you can say, and I'd like for DMA channel 0 to start when DMA channel 1 finishes. And the two will ping pong back and forth forever. And by the way, the control registers of the DMA channels are themselves memory mapped. So you can have a DMA channel write to the control register of another DMA channel, change what it does, and trigger back to the first. Is this starting to sound like a Turing machine to anyone? A little bit? These are Turing complete. You can do incredibly sophisticated things with just DMA channels And if you start writing to the control registers of other DMA channels, it gets really twisted. But you can definitely do it. You can do all this stuff. And they have crazy bandwidth. You can perform one read access and one write access up to 32 bits wide every clock cycle. Out of the box, this thing's running at 125 megahertz, 125 million clock cycles per second, and you can overclock it. You can take it up to 250, and that's just fine. And we have 12 of these channels, 12 independent channels, all of which can write to the control registers of all the other ones, all of which can be chained off of the other ones. So if you set these things up, you can have data just flying around through the system at unbelievable speeds, and the CPUs have exited main. They aren't doing anything. So how much time do we have? Let me show you a quick, simple example of this. And then I'll show you how this is used in the FFT example. So let's look at the DMA demo here. And I just want to show you, so all of this code, most of this code looks familiar. You can see that we're setting things up in a way that looks an awful lot like the DDS example. In particular, if we jump down to main, initialize stdio, set up an SPI channel, build a sign table. We're building a second table now, which we're calling DAC data. It's just as long as the sign table, and it contains all the amplitudes of that sign table, but with those DAC control bits already in place. So each element of this DAC data table is 16 bits wide. DAC expects 16-bit transmissions, and unlike last week, where when you were doing the SPI transmissions, right before you did it, you masked in the control information. We're storing the data with the control information already in place. The reason for that is we're going to set up a DMA channel to just move through this table and shuffle data out to the DAC. And if those control bits are already in place, the data is good to just be sent away. You don't have to do any manipulation of it. And then we set up a couple of DMA channels. We're going to call one of them data channel. That's going to be DMA channel 0. The other one's going to be control channel. That's DMA channel 1. And I just want to walk through one of these configurations. So lines 76 to 90 here are configuring. Actually, no. Let's start with the second channel. Lines 93 to 113 here are configuring one of these DMA channels. And you can see that the first thing that we're doing is getting the default configurations for that DMA channel. You can look up what those default configurations are. It's something like, by default, 32-bit chunks of data. By default, it's going to do all the transactions just as fast as it can, unpaced by anything. There's a bunch of default stuff that we then go in and modify to customize to our particular application. The first of those custom modifications that we do is we configure in line 94 there that we want for the transfer data size, the size of each transmission, to be 16 bits as opposed to the default 32 bits. Why? Because we're going to be talking to the DAC, and the DAC's expecting 16-bit transmissions. We are setting the read increment to true. What that means is that we'll tell the DMA channel where to go start accessing memory, and then for every subsequent transmission, it will increment its read pointer forward by 16 bits. So we'll say start at index 0 of this DAC data table, and for the first transmission, it'll access the 0th index of that array, and then the read increment will occur. It'll move forward 16 bits, so that for the next transmission, it's accessing the next index of that array. We're setting the write increment to false because we're always writing to the same place in memory. We're always going to be writing to the SPI transmit buffer. That never changes. The data that we're writing changes, but the place that we're putting it never changes in this case. We're going to pace this particular DMA channel off of a timer, and this sets the pace of that timer. And you can read about this in the SDK guide, but there's a little equation here, x over y times system clock. System clock is 125 megahertz. These two arguments are the numerator and the denominator of that equation. So it allows for you to configure the speed with which you want these transactions to occur. We're setting this up to send transmissions at 44 kilohertz, which, by the way, is I believe, faster than you can take one of those timer callbacks, or at least it's right on the edge. Maybe it's 48. In any case, we're benefiting from the fact here that this is all taking place automatically. We're not spending any CPU time. We are configuring the data request signal here. Remember that I was talking about how you can configure a DMA channel. You need to tell the DMA channel when it should do each transfer. You can have that be attached to the ADC channel. In our case, we're attaching it to this internal timer, which every other data request line has a nice readable human name. This one, you have to go into the data sheet, and it says, oh, if you want to use this particular timer, it is 0x3b. It's a little bit cryptic, but that's okay. And then we are chaining this channel. So what we're saying is, when channel 2 finishes, this one that we're configuring, automatically start the previous channel. And we'll look at what that other channel is doing in just a second. And then we set everything up here. So we say, okay, we're going to configure this channel. Here's the configurations that we just created. Here's our write address. We're going to write to the SPI data register. Here is the initial read address. The name of an array is a pointer to the first index of that array, right? Remember that? So this is a pointer to the start of that DAC data array. This is the number of transfers that we'd like to do. It's the size of that array. And if this were true, it would start the DMA channel right away. We're going to start it on our own in just a second. So this sets everything up. So that's the first one. And then the other channel writes to the control register of that one that we were just looking at. In particular, the only differences here are it's going to do 32-bit transactions because the control register is 32 bits wide, so we want to send 32 bits. No read incrementing, because we're always going to be accessing the same place in memory to send the data. No write incrementing, and we're chaining it to the first one. And you can see that the address that this channel is writing to is the read address of the other channel. So the way that this works is channel 2 here, this one, we're going to start it. It goes through that whole table, sending information out to the DAC. When it reaches the end of the table, it automatically chains to this channel, which puts its read pointer back at the beginning of the table. And then this one's chained to the other one, so it just starts it over again. The read addresses don't wrap. So if you want to reset the read or write address of a DMA channel, you have to have another DMA channel reconfigure it. There is a way that you can do it in the case that the amount of data that you're transferring is a power of 2 and that data is aligned in memory, but that's just so bizarre. I would say the most straightforward way to do it is to reset it with another DMA channel. Okay, so this, if you program your RP2040 with this in lab and plug in a speaker, it's just producing a tone. But what's interesting about the way that this is producing a tone is we exit main. So there's sound coming out of the speakers, and we have exited main. There's no code running on either of the processors. It's all just DMA channels accessing memory. So if we take a look at the code for your checkout, we'll find something pretty similar. So let's scroll down to main. And beneath all of our ADC configurations that we were just looking at, we'll find our DMA configurations. And similar to before, we're setting up 2 channels. One of those channels is going to be moving data. The other channel is going to be resetting the first one. Let's just take a look at the ADC sample channel. And you can see that we're configuring the channel to do 8-bit transactions. Recall that this is because we've configured the ADC to shift out the least significant 4 bits. So the ADC is putting 8-bit samples in the FIFO. So we want for this DMA channel to move all 8 of those bits. We have turned off read incrementing because we're always accessing the first index, or the first element rather, of the ADC FIFO, always the same place in memory. So we don't need to increment our read pointer. But we are actually incrementing our write pointer because in our case, rather than moving through an array that we're reading and sending it to the same place in a hardware peripheral, what we're doing now is always accessing data from the same place and filling up an array. So we want to increment our write pointer so that the first time this runs, we're filling up index 0, and then it moves to the next index of the array and fills it with the next sample, and so on and so on and so on. And Unlike previously, where we were setting this data request line to that timer that we configured, we're now saying we want a transaction to occur when that data request signal from the ADC asserts. It will do this. We've configured the ADC previously such that it does that whenever there is one sample in the FIFO. So a sample appears, data request goes off, it triggers this DMA channel. And then we just set up the last thing. So this is the channel we're configuring. These are the configurations that we just set. Our destination, we can look at this up in the code in a moment, but this is just a character array. It's a big array of 8-bit characters. This is where we're going to be dumping the data. This is where we're reading from. It's the FIFO for the ADC. This is how many transactions we want to occur, our number of samples. I think this is set up to 256, I think, some power of 2. And we don't want to start this just yet. We'll start that in a second. The other channel here, similar to before, resets the first one. In this case, we aren't going to be writing to the read address. We're going to be resetting the write address because that's what's getting incremented. So as soon as this has done num samples transactions, it triggers this next channel. This next channel, as you can see, is set up to reconfigure the write address of the first channel back to the beginning of that sample array. So channel 1 fills up the sample array, triggers channel 2, which points it back to the beginning to fill it up again. And you can see that the control channel is chained to the sample channel. The sample channel isn't chained to anybody. This will only start sampling when we tell it to in software. And the reason for that is we don't want for it to start replacing the data in that buffer until we've copied it to another buffer to do some work with. So let's just take a look at that. So if we go up to the thread here, what you can see is the first thing that we do is start the DMA channel. So this turns on the DMA channel, and it's waiting for that signal from the ADC to say, I've got a sample. We then start the ADC, and the ADC is going to start gathering samples and putting them in the FIFO at the speed that we've configured, 10 kilohertz. Every time data appears in the FIFO, that data request line is asserted, the DMA channel grabs it and moves it to the next index in that sample array. Just writing stuff to the screen. Okay. The first thing that we do in this while loop that repeats over and over again is we wait for that DMA channel that's gathering the samples to finish. We wait for the full buffer to be filled up. Once the buffer's full, we go through and copy the data in that buffer into a second buffer that we're going to be running the FFT on. And as soon as we've done that copying, we restart the first channel. This is nice because we can be gathering the next buffer of samples simultaneously with doing an FFT on the previously gathered batch. So while we're computing an FFT, we're gathering the next batch of samples that we're going to be doing an FFT with. FFT fix, there's an FFT function up above that calculates the FFT on the gathered sample. The FFT, have you guys been introduced to the FFT algorithm in other classes? Okay. Incidentally, if there's a pretty extensive web page, if you care, that talks through where this algorithm comes from, starting with the sine cosine series. Okay, and then we go through, we compute the FFT. The FFT, as you know, it generates complex numbers, real and imaginary parts. We compute the magnitudes of those complex numbers to get a power spectrum rather, and we figure out where's most of that power in that spectrum live. So what's happening here? Once this is running, we're waiting for the DMA channel that's gathering data to finish. Once it finishes, we're copying all that stuff that it's gathered into a second array, and as soon as we're done copying, we're starting this channel up again to start gathering the next batch. While this is happening, this is non-blocking, so this just carries on. And then in the meantime, we go through and do math on the previously gathered batch of samples. In particular, we compute an FFT We calculate the magnitudes of each of the FFT outputs, the complex number outputs, and we figure out which bin has the most power in it, and we're printing that out. In your case, you're going to look for power at the cricket frequency bin. We go through, and in the event that we've gotten through all of this faster than it has taken to gather the next batch of samples, we sit and wait for that batch of samples to be finished being gathered, and then we continue on and do it again. By the way, many of you have gotten this running already, but I have this programmed with this FFT code. And what we'll see here is, so there's a microphone here. As I talk, you can see the FFT of my voice. What's my fundamental frequency? 175 hertz. It's kind of an interesting thing to know about yourself. Another one of those metrics you can track throughout your life. So in any case, this is just computing an FFT. And what you will do, let's go back to the laptop here. So in lab this week, I'm going to share my screen. So in lab this week, you are going to be integrating this code with your Cricut synthesis code. There's some things that you have to be careful of when you're doing that. Remember that what you're trying to do is detect each core is trying to detect other cores' crickets. So it's trying to detect cricket chirps being generated. Core 0 is trying to detect cricket chirps being generated by core 1, or alternatively by other folks in the room, right? In order to do that, when you start gathering the next batch of samples, you need to know a few things. In particular, you need to know which state are you in your interrupt service routines. Is core 0 in the state that's generating a cricket chirp? Because in that case, you can expect that you are going to find a cricket chirp in that FFT, but you have to know that, yes, I'm seeing a chirp, but I also know that I am generating a chirp. So that's my chirp, or it's a chirp that I'm synchronized with already. So I'm not going to take any action in connection with that sound. Alternatively, if you discover that you're in the chirp pause state, that is to say you're between chirps, and you gather a batch of samples, and you find a cricket in that batch, you know you didn't make that cricket chirp. That's somebody else's cricket. And next week, you'll implement an algorithm that you take an action in response to that. In particular, you adjust the amount of time to your next cricket chirp by a little bit. And you do so in such a way that over a little bit of time, everybody synchronizes with everybody else. And the way that we're going to, there are perhaps more elegant ways to detect a cricket chirp. The way that we are going to do it is you're going to do this FFT. You'll find the max frequency, that is to say the frequency with the max power, the frequency that is the loudest. And if you notice that the frequency that is the loudest is the one associated with 2300 hertz, we associate that with a cricket chirp. So what that means is that this will work really nicely at your own lab bench, where there are speakers right there, and it will certainly be the case that the loudest frequency is the one being generated out of the speakers. When we try class-wide synchronization, we might just all have to keep our voices down, because we could introduce a little bit of noise here if we weren't careful. There are ways that we could do this more robustly, but for our purposes, this is okay.
Use a wider range.
Yeah, that's the other thing too, is look at the bin associated with the cricket, but give it a little bit of buffer too. If the biggest power is within, 2 or 3 bins of the one where the cricket should be located, you say, okay, that's a cricket. That's a cricket. Questions about this? Okay. So probably not this week, probably not next week, but sometime when we have some time that's a little bit flexible in lecture, I'm going to talk through some more sophisticated DMA examples to try to illustrate a bit further the benefit that you can get from clever utilization of these things. Okay, I will see Wednesday folks very soon, and I'll see the rest of you on Friday.